Thank you for the invitation. And today I will speak about my joint work with Sasha Bufetov, where we tried to understand behavior of determinantal point processes in the space of trajectories, mostly working with the sine process. So initially we wanted to prove something like the Donsker Invariance Principle for the sine process, but finally we find that nothing as Brownian motion appears, but we found a completely different type of behavior, type of asymptotic behavior. So, as I've already said, today I will speak mostly about the sine process, and if something holds for some different determinantal process, then I will mention this. The sine process is the determinantal process given by the following well-known kernel, and we are interested in the asymptotic behavior of the following just very standard random variable, which is just the number of particles hitting on the interval 0n when n is large. When n is large. So it's well known that this random variable satisfies the central limit theorem. First, it was proven by Kostin and Lebowitz in 95. This is just the central limit theorem in standard setting. So they considered the random variable, which I'll denote by xi n, which is just the number of particles on the interval 0n minus its expectation divided over square root of the variance And then they proved that this random variable converges in distribution when n goes to infinity just to the standard normal law. As in the classical central limit theorem for a collection of identically distributed independent random variables, here the expectation grows just linearly, as it's just equal to n over pi due to the stationarity of the sine process. However, there is a significant difference with the classical central limit theorem. This is that the variance grows unusually slowly. More precisely, it behaves when n is large as pi to the power minus 2 logarithm of n. However, the central limit theorem still holds. Since that time, the central limit theorem was proven for a large class of determinantal point processes and for rather large class of observables, in particular by efforts of Soshnikov. And it's well known that for many dynamical systems for which we have the central limit theorem, we also have the Donsker Invariance Principle, which states that, roughly speaking, trajectories of the system can be approximated by the Brownian motion. And the question we asked is if it is true for this random variable or it is not the case. So in which sense can we speak here about the Donsker Invariance Principle? Just in the classical one, we consider our number of particles, our random variable, our number of particles in the interval 0n under the sine process, and we insert the time t here, where we assume that time, say, between 0 and 1, and we want to study this object as a random process with time t in some space of functions, say the space of continuous functions. Yes, of course, this isn't a continuous function, but slightly modifying it, you can make it continuous, just as in the classical Donsker Invariance Principle. So, of course, I should normalize this random variable. The correct normalization is the same that in the central limit theorem. So I should subtract the expectation, and then I should divide over the square root of the variance. Also, of course, I should take the variance not of the number of particles on the interval 0 tn, but I should take the variance number of particles on the whole interval, so that I write directly the asymptotics of this variance. And we ask the first question, if it is true, as in the classical Donsker Invariance Principle, that this random process, xi tn, converges in distribution when n goes to infinity to the distribution of the Brownian motion and the answer is no. The answer is no. We find that nothing as Brownian motion arises here.
Tau in the denominator.
Tau?
Tau.
Sorry, it is pi. This is pi. This one?
Yeah.
Yeah, this is pi.
So there's no tau.
Hmm?
No tau.
No tau. No. Tau will be in a minute later. Yeah. So we find that this is just some constant. Yeah. We find that nothing as Brownian motion arises.
That actually follows from your theorem, or the constant level is because the scaling is wrong. If you look at the variance, it's like t equals 1/2. For this theorem, you can see that it's not what Brownian motion is.
I mean, yeah. The reason is this logarithm in the denominator. Yes, the reason is this logarithm. So this logarithm doesn't have any influence on the Central Limit Theorem. However, for the behavior of trajectories, it has crucial influence. And then we ask the question, what do we have instead? What do we have instead? Can we specify the limiting behavior of trajectories of our process? And first that we find that due to this logarithm in the denominator, behavior of trajectories is extremely irregular. I will explain it later in more details. So in particular, the limit cannot be specified in the classical sense, so it does not live in any separable metric space. That's why instead of studying this process, we will study the time integral of it in order to regularize the dynamics. And it turns out that the limiting behavior of this time integral can be specified. And in order to state the result, let me introduce some notations. First, I fix some moment of time tau, which is between 0 and 1, which is not random, just deterministic. And then I set eta n to be equal 1 over tau, integral from 0 to tau of our process. So just the averaging of our process over the interval 0 tau. And then I represent my integral as a sum of two terms. The first one, this is just linear in time process with angular coefficient eta n, and the second one is some process ztn divided over square root of pi to the power -2 logarithm of n. So this is just the same normalization that I have here. And this formula is a definition of the process ztn, so I choose the process ztn in such a way that this holds. And our main result is the following theorem. It states that we have the weak convergence of joint distributions of the random variable eta n and the random process ztn when n goes to infinity to the joint distribution of some random variable eta and random process zt. The convergence holds in the space of real numbers times continuous functions on the interval 0, 1. On the interval 0, 1, so it corresponds to the component eta n and continuous functions to the process ztn. And here eta and the process ZT are independent, eta normally distributed with parameters 0, 1/2, and Zt is a centered Gaussian process with the covariance matrix given by the following formula. This formula is rather long and complicated, but the point is that we just compute it explicitly, so we know the process Zt in explicit way. So it has the following form. It's equal to some function w of st plus w of ts, where w is given by the following expression. This is equals to 1/2 h of t minus s. What is h? I will say in a minute. Minus 1 minus s over tau h of t minus s over tau h of t minus tau, and plus t over tau 1 minus s over tau times h of tau, h of t, sorry, where h of t, this is just t squared logarithm of the absolute value of t. So we have such a covariance matrix, and the last item of the theorem says that, I will not state it rigorously, but informally it says that the rate of convergence of the distribution of eta n to the distribution of the random variable eta is not less than 1 over square root of the logarithm of n. In which sense we speak about the rate of convergence? Just it means that the rate of convergence of cumulants is not less than 1 over square root of the logarithm of n. So this is the result. Now let me explain what does it mean. It means the following. So we have our integral of the process xias and ds, and the theorem says that this process can be decomposed to two components. The first one is just a linear in time process, which is given by t eta n, and asymptotically this process is governed by the real line, by the line with normally distributed angular coefficient t eta. The deviation between these lines due to this item of the theorem is not more than 1 over the square root of the logarithm of n. And the second component, these some fluctuations which are asymptotically given by the process zt over square root of pi to the power minus 2 logarithm of n, where zt, this is a Gaussian process which we know completely due to this covariance matrix. The size of these fluctuations is the same as the deviation between the linear processes, but this shouldn't confuse because these are some nonlinear, rather complicated fluctuations, and these are just two linear processes. Moreover, the fluctuations become independent asymptotically from this linear process. And also we have some smaller order correction due to the convergence of the process Ztn to the process Zt. So we have such a strange behavior. We also have some I would say statistical interpretation of this result. It says that if you want to predict the behavior of your process, you need to know it at arbitrarily small time tau. So if you know the value of this integral at arbitrarily small, the realization of this integral at arbitrarily small time tau, then you know the process Etn, then you know this linear process and the Gaussian fluctuations that I just also known by this formula.
So can I have a question?
Yeah.
If your fluctuations are the same size as the error,
Yeah.
then how can you tell what is fluctuation and what is error?
No, I mean the point is that this is the error between two linear processes. I mean, okay, you can take something from this process and add to the fluctuations, but now it will be more the linear process. So what is bad if you have the sum of two processes which are of the same size, and if one of them can cancel another one, then that's the problem. But here it's impossible because you have a linear in time process and then rather complicated nonlinear fluctuations.
What's the smoothness of trajectory with respect to this Gaussian map? Also,
let me think about this. Yeah, I think it should be it should be Hölter. I think yes, I think so, yes.
Can I
Yeah.
So this Zt is a kind of generalized process?
No, the T just continuous random process
Okay.
which is given by such covariance matrix. Hmm?
Okay. Only have, yeah. So you have to integrate against the test.
So can you actually say what is the theorem? Because this is not well defined, right?
Yes.
This distribution, So the way you write this, right? This is not well defined because
Why?
you could write some other Zt.
No, wait. This is once I defined the random variable Etn. This is well defined. Okay.
Write it like that.
Because just
Yes.
I found this process
And so
from
then
from
for the
this
Zt,
formula. For the T, of course, it depends on the choice of time tau. So you can see this here because in the covariance matrix you observe this tau, but just explicitly.
Okay. No, that's great.
So when T equals S, everything should be the first term. Okay. So it's just 0. Yeah.
Distribution of eta does not
Distribution of eta does not depend on tau. Yes, that's the point. It doesn't depend on tau. But of course, the random variable Etn depends on tau, and that's why the previous question that T also depends on tau. But eta and the T becomes independent. So under the limit you have two independent objects.
Why don't you just take tau equal to 1?
Yeah, I could take tau equal to 1, but just I like this statistical interpretation that you can take tau to be arbitrarily small, and then after some arbitrary small time, you know the behavior of your process.
Yes, but I mean, W is something.
Yeah, it would be slightly simpler. You should subtract 1 here. You will not have sum of terms.
Well, W becomes very bad when 2 goes to 0. So. want to let.
Yes, that's it. But I don't want to let it go to 0. Just I can take it small. So of course, if I do not have a lot of information, then I have rather bad result. I mean, if I do not wait for a long time to determine this process, then I have not very good statistics, but still I can determine it. So this is the result. What is about the generality? The result is true for the sine process. The marginal convergence eta n to eta, so the main order asymptotics that the process is governed by linear process holds not only for the sine process but for general determinantal process with logarithmically growing variance. So in particular it holds also for the Airy and Bessel processes. The only thing that we use there is this square root of the logarithm in the denominator. But concerning the convergence of the process ztn to the process zt, here we crucially use that our process is the sine process probably, but by some another method it can be generalized. But I mean our method doesn't work for different processes. I will explain later on why. So my plan now is the following. First I will explain some motivation behind this theorem, how one can see that behavior of trajectories of the process xi t is very irregular, so that you should consider the time integral of the process and not the process itself, and then why you need to look at the second order approximation and not restrict yourself, but just the first order asymptotics. And then I will give the proof of the result, and if I have time, but I don't think so, I will state another result, which, roughly speaking, it states that a large class of processes has the same asymptotic behavior. These processes are, the large class of observables. These observables are some ergodic integrals under the shift operator on the space of configuration under the sine process. And now let me pass to the motivation. So let us forget about this theorem. Let us just remember that we have such a random process xi tn, and we want to study its asymptotic behavior when n goes to infinity. Of course, the first thing that you do, you study its finite dimensional distributions. About this, we have the following lemma: for any times t1 and so on td between 0 and 1, we have that the finite dimensional distribution xi t1n and so on xi tdn converges weakly when n goes to infinity to the distribution of the random vector xi t1 so on xi td, where xi t1 xi td, I will denote this vector by xi. Xi is a centered Gaussian random vector with a covariance matrix given by the following relation: expectation of xi ts of xi t xi s equals to 1 if t is the same as s, and equals to 1/2 if t is different from s. So this is just a generalization of Kostin and Lebowitz central limit theorem. But what we find that the limiting distribution is independent from the choice of times completely. And this is a simple consequence of the fact that here you have the logarithm in the denominator. In fact, just some simple computation to get this limiting variance. But in particular, it means that nothing as continuous process can arise. Because if you have two moments of time and one tends to another, then the rate of decorrelation doesn't go to 0. It stays the same. So we cannot have a continuous process. But what then can we have in order to understand it, let us represent the distribution of the limiting process xi as the distribution of sum of two processes. The first has the same component at each side, which is eta. I will say in a minute what is this. In fact, it's the same eta that is a theorem. And the second vector is gamma t1, gamma td. Here eta and gamma t1, so on, gamma td has normal distribution, the same normal distribution with parameters 0, 1/2. It's the same that in the theorem. And also all of them are independent. So this is just simple computation. You should verify that the variance of this sum is the same that this one. Then we expect that if this we expect that if the limiting behavior of the process xi tn can be determined, then it should be governed by the sum of two processes which have these finite dimensional distributions. So the first one, of course, this is just a constant process which is equal to eta at each instant of time, and the second one is the process gamma t, where gamma t is a centered Gaussian process with a covariance matrix gamma t, gamma s equals to 1/2 if t equals to s, and 0 if t is different from s, because of this distribution. But the problem is that such process gamma t is not defined in the classical sense, because you have a continuum collection of independent identically distributed random variables at each instant of time, so it doesn't live in any separable metric space. That's why it's clear that we cannot define this limiting dynamics in the classical sense, so we need to somehow regularize the dynamics. That's why we need to. That's why I, instead of studying the process itself, I study its time integral, and of course I expect that it converges when n goes to infinity to the time integral of the right-hand side. But this time integral is just eta t plus integral of the process gamma s ds. Here we expect that this integral can be somehow defined. You can draw an analogy with the white noise, which isn't defined in the classical sense, but its time integral gives nice process, which is a Brownian motion. And trying to realize this strategy, we prove the proposition, which says the following: for any integrable function phi on the time interval 0, 1, if we integrate our process against this function, then this integral in distribution converges when n goes to infinity to the distribution of just eta, where eta is as above, times integral times averaging of the observable phi. So in particular, if you take phi to be equal to the indicator function of the interval 0, 0s, then here we get exactly this integral, and this equals exactly to eta t. So we do not observe at all this integral, and I mean, if you can define it, then just by 0. And in fact, the reason is rather clear, is that the difference of the process gamma s with the Brownian motion is that it has only finite variance. So it oscillates very fast since it's completely decorrelated in time, but not with very large amplitude. And that's why under the integration over the interval 0t, it's just averages out. So in principle, in fact, this proposition just implies the main order asymptotics in the theorem, the convergence of eta n to eta, with such a choice of the observable phi. But still, we lose a lot of information. We lose a lot of information because at the level of finite dimensional distributions, we observe some process gamma t, but at the level of studying the trajectories, we lose it completely. So we would like to recover somehow the influence of this process in the asymptotic behavior. So what are we doing to this end? We note that the fact that this integral, informally that this integral equals to 0, this resembles the laws of large numbers, because you have something like a sum of independent identically distributed, very large sum of independent identically distributed random variables, which are centered. So of course it converges to 0. So then we have just naive idea to look at the central limit theorem scaling. Maybe we will see something there. And it turns out that yes, that we can recover some trace of this object in the central limit theorem scaling. And actually this gives us just our theorem. So this gives us the smaller order asymptotics, this one. So this is some motivation behind the theorem. Now let me pass to the proof, but the proof is based on some general version of the central limit theorem for linear statistics. So let me first formulate this central limit theorem. Let us take some real function f, which is bounded, measurable, and has compact support, and let us denote by SF and the linear statistics corresponding to this function. So the sum over all particles from the configuration x of the function f of x over n. Here x, this is just the configuration of particles on the real line. In particular, if f equals to the indicator of the interval 0, 1, then SFN, this is just the number of particles on the interval 0, n. We have the following theorem. Let two functions f and j, which are real, bounded, measurable, with compact support, compactly supported. And let us assume that first the variance of the linear statistics for the function f grows to infinity when n goes to infinity. And second is that the function j is sufficiently regular so that it belongs to the Sobolev space h1/2 plus epsilon for some positive epsilon. So this is a Sobolev space. Then we consider the following random variables: xi fn, which is equals just the variable which one considers when proving the central limit theorem for the linear statistics SFN. So I subtract the expectation and I divide over its variance. And xi jn, this is just the same for the function j, but without the normalization over the variance. And then we have the weak convergence. Then we have the weak convergence of the joint distribution of the vector xi Sn, xi Jn when n goes to infinity, to the joint distribution of some random variable psi fn, psi f, psi j, where psi f has normal distribution with parameters 0, 1, and psi j has normal distribution with parameters 0. And here you have, I will not write this explicitly, but this is just something like h1 half 0, 0 norm of the function j. So this is the result. So we have such central limit theorem. In fact, what it affirms? It affirms that when if we look first at the convergence of the component psi fn, then the only assumption that we need, this is that the variance grows to infinity. Then we have central limit theorem in standard scaling, is a generalization of the Gaussian and Lebesgue central limit theorem. It was in some less generalities, it was proven by Soshnikov. With such generality, this is the result of myself and Sasha. And for the second component, the only assumption that we need, this is some regularity of the function j. Then, in particular, due to the Sobolev embedding theorem, function j has some is continuous. So when n goes to infinity, the function j over n it has very long tails. And due to some cancellations, we have a central limit theorem without any normalization. Results of this type were first obtained by Shpon and Soshnikov for some related system for C1 smoothness. With such smoothness, it's obtained by myself and Sasha, but Soshnikov claimed that this holds for h1 half smoothness, in fact, but we can get the result only for h1 half plus epsilon smoothness. And this joint convergence is also due to myself and Sasha, but of course we use the methods developed by Soshnikov. And also this theorem holds in many dimensions, so you can take some number of functions f of this type, some number of functions j of this type, and then you'll have similar result. So now let me explain the proof of my theorem 1, which is the main theorem. So we need to prove the joint convergence of the random variable eta n and random process ztn to the joint distribution of eta and zt. To this end, let us just look at the random variable eta n to its definition, and let us note that eta n just equals to some linear statistics sfn minus expectation of sfn over 1 over square root of pi to the power minus 2 variance of sfn, and ztn equals to the linear statistics corresponding to some function jtn without any normalization. What are the functions f and j? I will write down the function f. This is just the integral from 0 to 1 of the indicator function of the interval 0s ds, and the function j can be computed in a similar way. I will not write it down. It's just you need to look at the definition of your random variable eta to know this definition of the process psi Sn, and then remember that the indicator, that the number of particles on the interval 0n is some linear statistics. And in fact, that's it. Then we note that the variance of the linear statistics Sfn grows as 1 over 2 pi squared logarithm of n, and then that the function h, that the function j J belongs to H1. So we are exactly in the setting of our central limit theorem. And then applying the multidimensional version of this central limit theorem to the function, to the family of functions f and jt1, jtd for some instance of time t1, td, we find that due to this central limit theorem, distribution of the random vector eta n, zt1, and so on, ztd, converges when n goes to infinity to the distribution of the random variable eta, zt1, and so on. Ztd, where eta and zt1, ztd are exactly from the theorem. And you can compute the expectation, the covariance matrix just by this formula. It's some many-dimensional analog. So now we have just convergence of finite dimensional distributions, and then to pass from the convergence of finite dimensional distributions to the convergence in the space of functions, it's just very, very standard, and the classical Donsker invariance principle. You just need to prove that due to some regularity of the function gt in t, the family of measures is tight, and then you pick up some convergent subsequence, and it's completely determined. Its limit is completely determined by the finite dimensional distributions which we know. So we get the desired conversion. So we see it's completely based on this central limit theorem. And where do we use it? That our process is the sine process. In fact, we use it only once here when we prove the central limit theorem for regular statistics, because there we are based on some combinatorial identity which is due to Soshnikov, and it is specific for the sine process, probably by some another method. It can be generalized for larger class of processes, but for the moment we don't know how to do this. So this is actually the proof of the result, and I think that my time is finished. So thank you.